Imagine a vast, churning ocean. A colossal ship needs to stay perfectly still, not an easy task. Waves relentlessly push, winds constantly blow. How does it achieve this feat? Meet the Kalman Filter. It is a remarkable mathematical tool, an unseen intelligence, guiding the vessel with precision. This filter is the brain behind dynamic positioning, or DP systems. DP systems allow ships to hold their position and their heading automatically, without anchors, just using thrusters. The Kalman filter processes information. It tells the thrusters what to do. Minute by minute, second by second, it is a constant, subtle dance of calculation and correction, a truly smart navigator. Why is such precision so vital? Consider the tasks these ships perform. Delicate underwater construction, supporting offshore oil and gas platforms, laying deep-sea cables for global communication. Even a small drift could be disastrous. Safety is paramount. Efficiency is crucial. The stakes are incredibly high. Accuracy is not just a wish, it's a necessity. So, how does this marvel of engineering work? It's not some unknowable magic, it is the power of mathematics. Specifically, statistics and control theory. The Kalman filter makes predictions. It estimates where the ship should be. Then it compares this with real sensor data. It learns from any differences and refines its next prediction. A continuous cycle of learning and adapting. The Kalman filter, for all its brilliance, cannot work alone. It needs information, constant streams of data. These are its eyes and ears, its senses reaching out to the world. Multiple sensors provide these vital clues. Each tells a part of the story. Of the ship's interaction with its environment, the more diverse the information, the better. The filter thrives on rich data. One key input is DGPS. That stands for Differential Global Positioning System. Satellites far above Earth send signals. These signals pinpoint the vessel's location. DGPS improves upon standard GPS accuracy. It uses ground-based reference stations to correct for atmospheric distortions and other satellite signal errors. It gives a global position, but even this can sometimes be imperfect. Then there's the HPR, Hydroacoustic Position Reference System. This system uses sound waves underwater beneath the vessel. Transponders are placed on the seabed. The ship sends out acoustic pings. It listens for the replies. Timing these replies tells the distance and thus the ship's position relative to the seabed, a local independent check on its location. Many other whispers contribute. Wind sensors measure the wind speed and direction. This helps predict how wind will push the ship. Gyroscopes and motion reference units, MRUs, are vital. They sense the vessel's roll, pitch, and yaw, its heave, sway, and surge. Every tilt, every nudge, every rotation. All these pieces of data flow into the Kalman filter's calculating mind, forming a complete picture of the forces at play. The world of sensor data is not always perfect. Sometimes signals can be noisy or temporarily unreliable. Perhaps a satellite signal is weak or an acoustic echo is muddled. The Kalman filter understands this reality. It doesn't treat all information equally. It is a discerning judge of data quality. It knows that some whispers are clearer and more trustworthy than others. How does it achieve this discernment? It assigns confidence weights to different sensors. Think of it like a trust score, a sensor providing steady, consistent data. It receives a high weight. Its voice is amplified. A sensor behaving erratically or showing errors. Its weight is reduced. Its influence is diminished. This is a core strength of the filter. It sifts through the noise to find the most probable truth. This intelligent weighing creates a superior estimate. The filter combines all the weighted inputs. It produces a single, robust understanding of the vessel's true position and movement. This combined estimate is far more accurate and more reliable than any single sensor. Even the best individual sensor has limitations. The filter overcomes these by synergy. The whole becomes greater than the sum of its parts, a beautiful fusion of information. This weighting process is not static, it is wonderfully dynamic and adaptive. The Kalman filter constantly monitors each sensor. If a DGPS signal suddenly becomes noisy, its weight is immediately downgraded. If a previously erratic wind sensor stabilizes, its influence might gently increase. The filter is always learning, always adjusting. It strives to maintain the best possible estimate, even as the quality of its inputs changes. Consider the immense responsibility during cargo operations, transferring thousands of tons of equipment or precious liquid natural gas between a ship and a fixed platform or another vessel side by side. Even a slight unexpected movement can be catastrophic. Stability is not just desired, it is demanded. Precision is the bedrock of safety. There is no room for error. Lives and the environment are at stake. Here, the Kalman filter acts as a silent guardian. Its accurate position estimate is paramount. It allows the DP system to counteract every disturbance. A gust of wind, a rolling wave. The thrusters respond instantly, precisely, guided by the filter's wisdom. This maintains the vessel's exact location and heading, preventing dangerous drift or sudden shifts. It ensures operations proceed smoothly and, most importantly, safely. But what happens when a sensor fails? It is a scenario all complex systems must anticipate. Perhaps a DGPS antenna is obstructed, or an HPR transponder malfunctions. The Kalman filter is designed for such events. It doesn't panic, it adapts gracefully. It recognizes the unreliable input and significantly reduces its weight in the calculation. Other sensors then carry more influence. The system endeavors to continue safely. The real challenge arises with multiple simultaneous failures, especially if they affect key sensor types. If, for instance, all DGPS signals are lost, and the primary HPR system also fails, the filter will do its best with remaining data, but the accuracy of its estimate may degrade. The DP system might struggle to maintain position. This highlights the critical need for sensor redundancy and robust system design, yet even then, the Kalman filter's ability to manage partial failure remains its unsung heroism.